Hi, this is problem 19 of the AMC 12A. For some positive integers p, there is a quadrilateral ABCD with positive integer side lengths, perimeter p, and right angles at B and C with AB equal to 2 and CD equal to AD. How many different values of p, the perimeter, for less than 2015 are possible? So this is a little bit complicated to set up. And the one thing I notice is that we have right angles at B and C. So let me try to set this up inside a coordinate axes where I make this vertex B with a right angle, and we have vertex C with another right angle, and we have side length AB equal to 2. And now we have the condition that we can apply that length AD has to equal length CD. So here we can now choose the vertex D to have the coordinates x, y, and that sets up the problem quite nicely because that makes length CD equal to y, and we have AD equal to some length, and this all looks pretty convenient now, and BC is just equal to the coordinate value of x. So looking at the length AD equal to DC, we can set that up as the length determined by the Pythagorean theorem, and the length squared is given by y minus 2 squared plus x squared. So that's the length squared, and we know that the length squared is equal to y squared. And let's simplify that a bit. Y squared minus 4y plus 4 plus x squared equal to y squared. Cancel the y's, and we have x squared equal to 4 times y minus 1. And let's see, we can write y in terms of x now as x over 2 squared plus 1. So now we get some insights as to how we can choose x and y. And it looks like an integer value of x isn't quite good enough to make an integer value of y, but an even value of x is good enough to make an integer value of y. And that suggests the variable substitution calling z equal to x squared over 2, or excuse me, x over 2. And so now we see that for any integer value of z, we can generate the integer value of y and the integer value of x. So z looks pretty convenient because any integer value of z gives us a valid solution. So now let's try to apply the perimeter condition now. We want the perimeter, which we know to equal 2 plus x plus y plus L, which we know is equal to y. And let's see what that is in terms of our new variable z. So that's 2 plus x, which is 2z, plus 2 times z squared plus 1. And let's reduce that a little bit. 2z squared plus 2z plus 4. And now we can apply the condition that we want the perimeter to be less than 2015. Bring the 4 to the other side and divide by 2 gives us z squared plus z is less than this. Minus 4 divided by 2 is 105.5. Let's see, let's pull out a z. Z times z plus 1 is less than 1005.5. So let's examine what integer values of z satisfy this equation. So certainly z equals 1, 2, 3. These all work, and we seem to reach the threshold when z is roughly equal to the square root of 1005. So somewhere around 30, 31, 32, we're going to cross this threshold condition. So let's take a look at 30. So 30 into this equation is 30 times 31. That's 930. Let's try 31. 31 into this equation is 31 times 32, and that's 32, 96, 992. So that's okay. I think the next one's going to fail. Let's check. 32. 32 times 33, 66, 99, 1056. Okay, so this crosses the threshold now. And so this is not a valid solution because it violates this condition. And it looks like the total number of valid solutions we have are for z equal from 1 to 31, and that's total of 31 different values of p, and that's choice B. Anyway, kind of a difficult problem. It's important to recognize this important variable substitution and realize what are the constraints on x to create integer values for y, and that's one of the keys. So anyway, hope that was clear. Bye-bye.